This is video 9.2.2, and the goal of this video is to be able to write a hyperbola in standard form and to use hyperbolas to model situations. So we're posed with the following problem. We have an equation that we're told is a hyperbola, and it is not written in standard form. So we want to convert this to standard form by completing the square. And it's going to be very similar to what you've already done, but the biggest difference is the normal equation for a hyperbola we know looks like x minus h squared over a squared minus y minus k squared over b squared equals 1. Now, with the biggest difference being maybe, in fact, instead of the y being second, it might be first with the x. There might be some shifting there. But in general, we need quantity with x squared minus the quantity with y squared, or vice versa. So let's take a look at this. A couple things we notice. We notice the subtraction on the y squared. So that's beginning to make me think that the x's are going to come first. So I'm going to rearrange the x's first and put the y squared second. Okay, now I'm going to do the same process I've been doing for circles and ellipses. I'm going to complete the square on both the x's and the y's. We start with factoring out the x before, and then we figure out what's going to have to go in this box to complete the square. The same thing with the y, but notice I'm going to factor out a negative 9 y, negative 9 from the y terms. So that's going to make it negative 2y. So that's really important. You know, you're going to have to be extremely careful with your negatives. And I'm still going to have some extra quantity right here. Equals 29. So we are ready to figure out what those quantities are so that we can add them to the other side. It looks like we have over here, it's going to take a 4 because this could be x plus 2 squared with a 4 in front. So that would make me, I'm actually creating not just 4, but 16. So I'm going to add 16 to this side. Okay, let's do the same thing with the y's. It looks like the quantity of 1 will create a perfect square, a square with y minus 1 squared. But once again, I got to figure out what exactly it is that I created. And if you note here, it's negative 9 times 1. So I really created negative 9, so I need to create negative 9 on the other side. Okay, so these are really important small pieces that need to fit with the puzzle in order for us to get the right solutions here. Okay, so negative 9 on the right. So altogether, this will equal, if I add all these pieces up, I will get 36. And now I'm ready to finish it out by dividing everything by 36. So remember, your goal is to get the 1 on the right. If we don't get denominators over here, we'll find ways to do that. But getting the 1 on the right is the first thing you're going to do at this point. So it looks like we're going to get x plus 2 squared over 9. Because the 4 will cancel with the 36 and create a 9. And it's similar over here, but instead it'll create a 4. Equals 1. So there you have it. So there's your rule in standard form, so we can graph it and talk about things like foci and intercepts and so on. So let's take a look at the next example. So what's really cool about hyperbolas is they have many applications, and this is kind of a neat one. When comets are close to the sun, they have elliptical paths. Okay, so they get, and the sun is typically the focus. When they are farther away, they have a parabolic orbit, which is interesting. And those farthest from the sun have a hyperbolic orbits. And the sun is the focus for each of these orbits, and a vertex exists when the comet is closest to the sun. So these are it's kind of some interesting things that these travel, these elliptical, parabolic, and hyperbolic orbits as they travel near to the sun and shoot off into space. So let's take a look at a different type of application that takes us to the root of the definition of a hyperbola. So let's take a look at this problem. 2 microphones, 1 mile record an explosion. Microphone A received the sound 2 seconds before microphone B. What Where did the explosion come from? Other information that you will need. Sound travels at 1,100 feet per second, thus the explosion took place 2,200 feet farther from B than A. 1 mile is 5,280 feet. So let's think about this problem. We have, why is a hyperbola going to model this situation? So we have microphone A and microphone B, and they receive this explosion 2 seconds difference. Okay, so as you can see this little picture, this is the explosion, this little dot here. That's the explosion. And so you can see A is closer than B. That makes sense. Okay, but the question is, how far apart are these? What do we know about these green dotted lines? And the one thing that we do know is that the explosion took place 2,200 feet farther from B than A. So this distance here is 2,200 feet more than the other distance. Okay, 2,200 feet more than the other distance. And so remember, your definition of a hyperbola is where the difference between the two distances is constant. And in this case, no matter where we put this explosion on this hyperbola, so remember, hyperbola, every point on there is equidistant from the two foci. I'm sorry, not equidistant, it is the difference of the two distances is constant. And in this case, our difference is always 2,200. So again, how does that help us write a rule to model this situation? Because that's our goal here. And I know it doesn't say in the example, but our goal is to write a rule to model this situation, to describe the potential locations of the microphone. So another thing that we want to know about hyperbolas is, in hyperbolas, in this case we have an x-centered hyperbola, so our a value is underneath our x. In a hyperbola, these differences between these distances is always equal to 2a. And think about why. Remember these vertices? How they are a from the center of the hyperbola? So this point right here would be a distance of 2a from the foci. No matter which, would have a difference of 2a from the foci. So remember, the foci are going to be right here. Okay, so the difference between the two foci would be 2a, because this distance is constant, and the extra distance that this focus would have to travel to this point, let's say this is the point we're talking about, would be an extra 2a to get there. This distance would stay the same. I'll put that in green. So this distance would stay constant, so they're going to be equal in that way. But the 2a would be the difference. So we could call that c, of course, because that's kind of what it is. And we can see the difference would be 2a between the distance from here, which is 2a plus c, and the distance here, which is only 2a, which is only a c. So the difference between them is 2a. So going back, the a value is very much related to the difference between the two distances. So our a value, our 2a, is going to equal 4,400. So 2a is equal to 2,200 because that is how far the constant distance is going to be that describes this hyperbola. So that means my a value is 1,100. So we've got one part of our rule. We're going to center this hyperbola that models the situation at the origin, and we're going to write a rule. And we have to figure out b still. Okay, so we have the a value of 1,100, and we still have to figure out b. So then we think about the other relationships we know. We know that the c value is always equal to a squared plus b squared. And since our a squared is 1,100, we just need our c value and we could find our b. And remember, c is how far the foci are from the center. Well, the microphones are at the foci. They're the ones that are measuring that distance. So this right here, 2,640 feet, is our focus points. That's how far they are from the center. So our c value is 5,640. And then we're going to solve for b squared. So I don't want to bore you with solving for b squared, so I did that quickly on my own, and the answer is 5,531 feet. So that's what b is equal to. B squared, of course, is what we want to put underneath the denominator, but I'm just going to round it to the 5,531. And then I have a rule describing where that explosion might have taken place. Now, this is great. I have a rule to describe where it might have taken place, but it doesn't really tell me exactly where. I actually cannot find exactly where. It could be anywhere along that hyperbolic curve. It could be anywhere along that. So I'm not sure where it exactly exists, but I could figure out exactly where it exists if I had another point, another microphone, and another hyperbola that could describe where the explosion took place, and where those two hyperbolas intersect would be the point at which the explosion took place. So I'm going to give you a problem from the book to try for your checkpoint. It's question 61 on page 874. And you have this problem that's here. So page 874, number 61. So give that one a try. It's with the microphones again. See if you can set up the picture and the problem. Actually, you know what? Don't worry about that problem. We're going to cancel that. You don't need to do that problem. Just do the number one here at the checkpoint. So good luck bringing your questions to class, and we'll go over them.